Right, so today we're very happy to have Joakim Faergeman, who will speak about Motivic realization of rigid local systems of curves via geometric problems.
Okay, thank you very much. And thank you very much for the invitation. It's been a lovely pair of days so far. I'll be talking about Motivic realization of rigid local systems. Curves by the geometric Langlands correspondence. Langlands. Okay. So the setup is as follows. We start with X, a smooth quasi-projective variety. And let's suppose sigma is an irreducible.
What's the ground rule?
Say again?
What is the ground rule?
Oh, sorry, over the complex numbers. And sigma is an irreducible local system on X. It's an elidification. So it's just the map from the fundamental group of X to G and C. Okay. And the definition, we say sigma if there exists a family y over x such that sigma is a subquotient of, say, I derived push forward of the constant sheaf on y. So here I don't assume that f is, say, smooth and proper. So the push forward of the constant sheaf may be some constructible sheaf. And then I can take the outcome homology and look at some subquotient of it as a constructible sheaf.
But you want this on the whole of X, or you are willing to remove a few more terms?
I consider this on all of X, although I consider this sheaf as possibly a constructible sheaf. So an equivalent thing to say is that you could try to find some Zariski dense open inside of X in a smooth proper family so that the push forward was really a local system. In other words, we can talk more generally about motivic sheaves on a variety X. It's just those sheaves you can obtain by a pull back, push forward tensor Verdi duality and taking subquotients of the constant sheaf on a point. Just the thing. And then if you happen to be a local system this way, we call it motivic.
Sorry, I assume F is very much not assumed to be smooth. Is Y assumed to be smooth here?
You can assume that if you want, but in this case,
right, yeah.
In any generality one, essentially. Okay. Yes. So the motivating question here is when is sigma motivic? Given some local system, you would like to give some kind of characterization of when it comes from geometries. That's a very difficult question. being motivic implies a lot of properties, and certainly the following necessary conditions. Being motivic implies for example, that the local system is integral. So meaning we can conjugate the local system to land in the ring of integers of some number field inside GLN of C. It also has Hodge theoretic properties, so the local system will carry a variation of Hodge structure, for example, and it will be arithmetic. So in the sense that it would descend to tell elliptic local system on some model of X over a number field. In fact, the latter property is conjecturally equivalent to being motivic, but very much open source. Okay, yeah, so to spell it out, it's very difficult to go in the other direction. Namely, it's very difficult to give a condition on a local system that guarantees that it comes from geometry. One such condition, conjecturally, is the notion of being rigid. Let me talk a bit about this. We'll be in a slightly more general setup, so let's let G be a semi-simple algebraic group. Connected, yes. Both connected. Algebraic group. You can also assume that it's reductive. Its semi-simplicity is just to simplify the notation a little bit.
Over Q.
Over the complex numbers. Doesn't matter too much. And let's fix a smooth convectification of X, assuming good properties at infinity. So I want to complement be, say, a simple normal crossing divisor. And then for each component at infinity, di, let's choose a conjugacy class. O sub I inside of G. And now we can define so that log says G of X from OI. This is the moduli space of G local systems. By which I mean maps from the fundamental group to G, having the local monodromy OI at infinity, with local monodromy OI at the component di. Okay. We're just considering the moduli of local systems on X, and we want to, in the definition of rigidity, we want to fix some properties at infinity, some lattice properties.
You assume some analog of reducible.
Yes. You mean on X?
No, that the local test map to pi one does not factor to a parabola.
Not yet. I'll do that.
When you have a nice moduli space, or what kind of moduli space?
For me, this is say the modular stack of all such
Ah,
local systems, but yes, I'm being vague about space versus stack here. But in a second, we'll take the rigid local system in question to be irreducible. Okay. Yes, it's a definition. We say so at some point in log sys is rigid if it defines an isolated point. Meaning,
just topologically, you alone input on first.
yes. So soon we'll take X to be a curve, and then there will be always be smooth, but a priori, yes. Okay, in other words, the local system doesn't admit deformations with fixed conjugacy classes at it. It's maybe one remark is that if G is not semi-simple, meaning it's reductive but not semi-simple, we should also fix the abelianization of the local system in the moduli description. In the moduli description. All right.
What do you mean by the periodization? Not composing it with the map of G onto G minus central forest?
Yes, G onto its abelianization.
No, it goes onto.
Just I want to fix the induced composition. Like so.
You really need that. Okay.
I think it would happen for you want to.
Yeah.
I'm a little worried with your definition of reduced because at the intersection of two divisors, you have two commuting transformations, and this is well defined up to conjugacy also. That's maybe more precise than the separate monodromy around all divisors.
Yes, so I think I mean what I say. So at each I require the local monodromy just to belong to this conjugacy class.
In
Yeah.
the case of curves, you have the tangent space with the moduli space is given by an intersection cohomology.
That's right. Yes.
But will it be true here also?
Yes.
Then I understood.
Okay, so the conjecture I want to state is a conjecture of Simpson. On 92. Which says that if these conjugacy classes at infinity are quasi-unipotent, meaning the eigenvalues of any element in it are roots of unity, then any probably want irreducible rigid G local system is Motivic. By which I mean the following. So i.e., whenever you have a representation of the group, when you twist the local system by that representation, I want this to be Motivic in the sense I defined before. This is an honest sheaf, if you will, an actual local system, and I can talk about that being Motivic in this. It's over here.
You did not define reducible.
Not define the modular space of irreducibles local systems.
No, what-
Sorry, what it means. Okay, thank you, yes. Yeah, so irreducible here. Reducible means does not factor through a parabolic. Probably. Let's do an example. An example here, which is the main one that's relevant for us. Namely, if you take x to be puncture P1, P1 minus some points. Then its fundamental group, it's generated by elements A1 up to AN with a relation that their product is 1. So this moduli space of G local systems with fixed local monodromy is, well, it's the set of the space of tuples AI, the product of these conjugacy classes, whose product is 1. And we want to consider these tuples up to simultaneous conjugation when we consider representations. So in this case, one is a tuple rigid. So let's say, let's note that this moduli space has a single complex point, in which case we say that the corresponding local system is physically rigid. If, well, we would want that whenever you take two representations of two tuples, this product, you can find, this implies there exists some S and G that simultaneously conjugates each one to the other. Is a IS inverse equals BI. These AIs and BIs lie in the same conjugacy class, but rigidity here, strong sense of rigidity, only has a single point, means you can simultaneously conjugate one tuple to the other.
I don't want the BI to be close to AIs.
Say again, sorry?
You don't want the BI to be close to the AI.
I think I just want them in the same conjugacy class here.
And this is a new definition. It's not a.
That's right.
A previous definition.
This is a stronger notion of being rigid. Certainly, if the modular space has a single point, then that's isolated. And in fact, in the curve case, Contrary to the higher dimensional case, if you have an isolated point in this moduli space, find here, then it had to be zero dimensional. Then we're just a discrete set of points, possibly stacking one.
That's true for n in V, not only in VLN.
That's right.
Oh,
That's right. But only for curves. Yeah. And moreover, those points are smooth. Okay, so some history of this conjecture of Simpson.
So in Simpson's conjecture, you don't want the monodromy to be the student, so it's a bit stronger, no? Because you could have you could be inside a smaller municipal.
That's right. Yeah, I won't require that here. Got it. Okay, so some history of the conjecture of Simpson. First is that it's just kind of tautologically true for any variety when the group is abelian. So here it's saying that any rank 1 local system is Motivic exactly when it's torsion, it's finite order. When you censor it with itself enough times, you get the true representation. Secondly, the conjecture is true when G is, so for any quasi-projective variety, when you consider rank 2 or rank 3 local systems. So this is by, let's see, get the order correct, correlate Simpson. That's GL2 in 07 and Langer Simpson in 2016. I should say at least under the assumption that the rigid local systems are integral, which is known whenever the local system is cohomologically rigid. Like it's a smooth isolated point by work of Inouye. And the third situation, which is the one most relevant for us, is that the conjecture is true for X a curve when G is GLN, which is due to Katz in 96. Who of course did much more and completely classified rigid local systems.
Well, why not in sets of P1,
On
not on any curve.
right, but yeah, I should say if you have a curve, then rigid local systems, irreducible ones, pretty much only exist in the genus 0 case. So there's some, yeah, I should have said that. So in the genus 1 case, there's kind of very few examples. I believe in genus 2 and higher, there are none. And so puncture P1 is kind of the only example in that dimension 1 case. Yes. Okay, and so the theorem I wanna.
Because it's only for projective.
This is only for what, sorry?
X projective.
Ah, okay, thank you. So projective case. Okay, this is properly. The Langer Simpson is right. Thank you. Okay. And the theorem I want to talk about today is the statement that Simpson's conjecture is true for, again, X a curve and a general group G. Yeah, so I should say again, this classification of rigid local systems, it's through middle convolution, it's kind of complete in a sense, but it's at least not clear to me how to generalize it to a group that's not GLN, because it's kind of inducting on N here. So it's showing that any rigid local system was really obtained from a rank 1 torsion local system on the curve via an iteration of middle convolution procedures, which is a Motivic operation. Okay, and the method we're gonna do that with is using the geometric Langlands correspondence. Before I continue, are there any questions about the statement?
Jiwei Yun and his collaborators had an approach to this kind of motivic realization.
That's right, yes. So
maybe you'll tell us how it compares.
yeah, I mean, not too much. So thank you for bringing it up. Yeah, so I should say this idea that you can construct rigid local systems with favorable properties via the geometric Langlands correspondence is not new. It's appeared by work of Yun and Heinloth and etc. in 2010, and also before that. It's not, so the way they do that is by constructing the Hecke eigensheet corresponding to that explicitly. I'll talk more about that in a second. But the idea that it was kind of going in the other direction. So you want a local system with favorable properties. Maybe you want the geometric monodromy group to be an exceptional group or something like that. This is going in the other direction. This is taking a local system and arbitrary rigid one and proving it is motivic. I can return to that in a second. So let's establish some terminology, but are there any more questions? Okay. Yes, so now we'll take X all over the complex numbers to be a smooth curve. And I'll do something somewhat illegal. I'll make a simplifying, a stupid simplifying assumption. Which is that X is projective. The reason why I'm doing this is that I really believe that the goal of this talk in some sense is to convey how geometric Langlands in characteristic 0 can approach a problem in arithmetic geometry. And that just becomes infinitely easier in the ramified situation in terms of notation, not mathematics. The caveat being that there are really no rigid local systems in the unramified situation, but we're going to. It's the idea I want to convey. The strategy remains the same in the 10 case, it's just more annoying.
But is there any example or not at all? We always said it's a different understanding.
Yeah, maybe if X is an elliptic curve, it might be the only only one.
To be something abelian then.
Yes, yeah, then right. So the abelian case is somewhat. So if I want a reducible, I can't think of one, I suppose, outside rank 1 or something. Yeah. And in fact, we'll see that it kind of cannot occur from this geometric Langlands perspective, and the claim is that things work out in the same case with the same considerations. So let us recall the geometric Langlands correspondence. So we let G check be the Langlands dual group. And so there are two sides of the correspondence. There's the automorphic one, the Galois one. The automorphic will let one G check of X be the moduli space, or really stack, of principal bundles for the dual group on the curve. Clearly, this is already kind of hurting everyone because I'm doing G check on the automorphic side instead of the spectral side, but that's because I was interested in local systems unless I want that to be the G side. Yes, and then, so this is, we'll consider kind of the de Rham geometric Langlands correspondence. So the automorphic category in question is the category of D modules on this moduli stack. I should say everything here is derived for me. On the spectral side, Galois side, let's all right, LS G de Rham of X. This is the moduli space, so really stack of G bundles with a connection. GLN, this is just usual rank and vector bundles equipped with a connection, automatically flat in this case.
Don't assume some regularity.
I cheated and X was projective and so yeah, so when X is a punctured curve, I would want to consider connections with regular singularities. Yes.
And when you speak about the moduli, it's autonomic.
Arbitrary D modules. Arbitrary, yeah. So that's an interesting aspect of the de Rham geometric Langlands correspondence. Is you really consider arbitrary, very big and very scary D modules, including the sheaf of differential operators, for example. Okay. And then on the Galois side, we'll consider the category of quasi-coherent sheaves on this moduli of bundles equipped with a connection. And then the geometric Langlands conjecture, which is now a theorem, states that these two categories are equivalent. So that might not mean a lot for kind of an abstract statement. There are properties of it that pin it down. For example, the structure sheaf here goes to what I'll call W. W is for Whittaker. And if you take a delta sheaf, a skyscraper sheaf at a local system, this goes to a sheaf, goes to something, I'll call it F sub sigma, which is the Hecke eigensheaf corresponding to that skyscraper sheaf. You can regard the construction of these Hecke eigensheafs as the main part of the geometric Langlands correspondence. Let me say a word about how this is defined. So W here is the Whittaker sheaf. And it's motivic. You don't really need to know how it's defined. I'll write it just for sake of doing it. So it's by the following construction. Namely, you take the moduli of bundles on your curve equipped with a sorry, the moduli of n check bundles on the curve. Here n is the unipotent radical of a barrel of your group. And really we should twist it a little bit to get a canonical character of it. A1. This has an obvious map to Bunch check. And W here is defined as pull push of the exponential module. The exponential D module here is D module on A1 are requiring that the partial acts by 1. An analog of the arbitrary sheaf in the finite field setting.
Can you tell again what N is?
Yes, so N was the unipotent radical of a parallel in NG check. Yeah, let me stress that it's not so important what W is. There's just a claim that it's motivic. It was given by pull, push, or something. I know that that something was the exponential D module, which has irregular singularities, and hence cannot be motivic in this sense over here. But the claim is that the wildness goes away in this push. Okay. That explains what this D module is. Now for F sub sigma, let's recall that what Hecke functors are. So the geometric Satake correspondence, equivalence, gives Hecke operators indexed by representations of the dual group. So whenever you have a representation B of, sorry, I'm being confused, this is G now. Okay, I think that's, yeah, for every representation of G, we get a Hecke functor from D modules on G check to itself times the curve. So it's kind of a global version of the usual Hecke operator at a point of it. And F sub sigma, here's a Hecke eigensheaf. Eigensheaf. Meaning kind of an vector eigensheaf for this operator. So whenever you act on it by H sub V, you get itself back times the eigenvalue, which is sigma, twisted by V. Okay. Any questions about Hecke operators? Okay. So now let's make an observation.
These Faergeman properties are for specific if you have like active parameters, it's not stated this one.
So I can talk about a Hecke eigensheet with eigenvalue sigma.
Yes, but I thought that if your sigma some other parameter thing, you'll get shared by the.
Oh, you're talking about alpha parameters. Yeah. Sigma here is, did I state it anywhere? Well, I guess there's no kind of, maybe I should take sigma to be irreducible here, then that's not. But the statement still parses, so I think eigensheaf satisfies this condition. It just might be that if sigma is not irreducible, you can get multiple of these exactly relating to other parameters. Let me not. Yeah, so I've been getting into trouble multiple times by not assuming sigma is irreducible. So let me maybe always do that. So henceforth irreducible. Okay. Yeah, so let's make an observation. The observation is that the local system on X is motivic from some geometry if and only if its Hecke eigensheaf is motivic as a D module on Bungie check. And for sheaf or D module to be motivic, it just meant that it came from some kind of pull push of the constant sheaf in any kind of way you can imagine. And the proof of one direction at least is somewhat easy. So if the Hecke eigensheaf is motivic, well then when you apply a Hecke functor to it, this is f sub sigma times sigma v. This is motivic because Hecke operators, that's a geometric operation. It's some pull tensor push operation. Well then, okay, the product of these two sheaves is motivic as a sheaf on bond G check times X. And it's easy to see that the second factor also had to be motivic. Take a fiber where this is not zero or something. Okay. So just to summarize a little bit, the goal now is to take a rigid local system on the curve and then, given the geometric Langlands correspondence, prove that its Hecke eigensheaf is motivic.
Or maybe it's not relevant for you, but why is the other direction true?
Yeah, that's less obvious. So for GLN, say, there's explicit construction of the Hecke eigensheaf first into the mole, and you can just kind of see if sigma came from geometry, that construction itself was geometric. For other groups, it follows by this Bailenson spectral projector operation. So Bailenson defined a spectral operator, which is a Hecke kernel that has the property that whenever you act on D modules on bond G, you get a Hecke eigensheaf with that eigenvalue. It still remains to check that the result is zero or not. It's kind of the point of everything, but the claim is then that the Bailenson spectral projector is built out of sigma. So if sigma was motivic, then the projector was motivic, and then the eigensheaf would be motivic. Is the overall sketch, but that direction won't be relevant for us. We're just interested in proving F sigma is motivic. Okay, and let's do that now. So the proof of the main theorem goes as follows. So suppose now we have a rigid local system. Rigid and irreducible. What does that mean? It means that the moduli stack. splits up as a disjoint union of just the point. Let me be careful and say there could be some stacky factor to it, so it could have automorphisms. And then the other components. So I'll just call that log cis not equal to sigma. Which is an isolated point, gives you the point and the rest. And the point is now that the property of being isolated gives us a decomposition of the automorphic category now. So, in particular, the category of quasi-coherent sheaves on the moduli stack of G-local system splits as a direct sum as quasi-coherent sheaves just on the point, maybe with a stabilizer, and the rest. Right. And so now applying geometric Langlands, the category of D modules on Bunch check, these are equal, itself admits a direct sum decomposition, decomposed as a summand, direct sum of two subcategories. I'll call the first one just D modules on Bunch subscript sigma. This is the one matching the first summand on the geometric Langlands. And the other one, if Bunch not equal to sigma. This is the one matching the second. Just to summarize, the existence of an isolated point in log cis allows you to decompose the automorphic category into a direct sum with the property, main property, that by construction, objects of this category, which is just corresponding to quasi-coherent sheaves on the point, they are Hecke eigensheaves. With eigenvalue sigma. That is to say, a rigid local system gives you a way to produce Hecke eigensheaf with that eigenvalue. Namely, you just consider the corresponding summand of any given sheaf. Let me spell that out. So maybe as such, if we take the Whittaker sheaf, W from over here, this is what.
I ask you a funny question, somebody who doesn't know geometric Langlands, but when you work with Whittaker models, you have to be generic. How's that avoided here? Because in the classical case, that often is you lose a lot of automorphic forms which are not generic. So where's that handled?
Right, your question is, The question is,
Without
there are a bunch of automorphic,
without the trace formula at some.
right, so there are a bunch of automorphic forms that don't admit Whittaker models.
Yeah, so how are you dealing with that?
There are two steps to that. First of all, do I have the geometric? Yes. First of all, it's not quite quasi-coherent sheaves that should appear here. It's rather some enlargement of it. So maybe I'll write it out. Really, it's not quite quasi-coherent sheaves that appear in the geometric Langlands correspondence. It's some slight enlargement of it. I'll just write it for the sake of writing it. This category is the so-called tempered subcategory, setting inside D minus 1 by G. So what am I saying? I'm saying I lied, and you shouldn't consider quasi-coherent sheaves on the moduli stack of local systems. You should consider an enlargement. And this subcategory of quasi-coherent sheaves corresponds to exactly the tempered D modules. And the tempered D modules are those that do admit Whittaker models. Okay, that was the lie, in some sense.
You mumbled something about orthoparameters.
Yeah.
So,
Yes.
Okay.
Yeah. So
I assume you know that's all right.
Maybe one more thing. So a consequence of this statement is that cuspidal D modules always have non-zero Whittaker coefficient. And that's not true in the automorphic theory, as I understand it. You know, this before or something. And there's a geometric reason for this. So L packets, for example, are encoded in the stabilizer of local systems here. So I swept various things under the rug. One was this temperedness condition, and the other one is considering moduli spaces up to moduli stacks, and I think those are. Let's finish the proof. So where are we?
What does this index n mean?
Yes. Yes. So I guess I have a habit of just writing things and then taking the definitions for granted. This is a notion of coherent singular support. So there is a notion of singular support for coherent sheaves on things like quasi-smooth stacks, and this is what I'm alluding to here. This enlargement can be considered as accounting for orthoparameters.
I was saying I'm used to quasi-coherent to be the same as incoherent, so I
Right.
don't understand what is happening.
Yeah. So when the space you consider is not smooth, so for example, just simple things like the spectrum of dual numbers, quasi-coherent sheaves and incoherent sheaves differ. Witnessing the fact that some coherent modules have infinite resolution. Okay, so I just want to finish the proof here. So what is the idea? Is that if you're given an isolated point in the modular systems, you can apply the geometric Langlands correspondence to get a direct sum decomposition of the automorphic category with the property that one of the summands consists entirely of Hecke eigensheaves. Now take the Whittaker sheaf, that's the D module that corresponds to the structure sheaf. So any D module will now admit a direct sum decomposition, where now this is Hecke eigensheaf with eigenvalue sigma. Because any object in this category is, and it's also Motivic. Because it's a direct sum end of W, which was Motivic. So that concludes the proof. I would like to make some remarks at least, but how much time do I have left at this point? Have I gone over the time?
8 minutes.
We have 4:30.
5 minutes or something. 8 minutes, great, okay. Okay, so before I make the remarks, are there any questions about anything? It's the one thing I shouldn't hit delete. Hit Bungie, there we go.
Sorry, so how much of the equivalence do you actually need to run this argument?
That, I'm gonna touch on that now.
I have one question. So, do you see any difference between smooth points and non-smooth points? I mean, the fact that sigma is reduced. I mean,
Yeah.
not at all.
The argument would work in the non-smooth case, but for curves, any isolated point is automatically smooth, and so.
But otherwise,
This would work for rigid local systems that are not cohomologically rigid, for example. But I guess they just don't exist.
where did sorry. No, please.
When you speak of quasi-coherent, it's also in some Dirac category.
Yes.
And how do you handle Dirac category?
Yes, I should say maybe contrary to the statements that the geometric Langlands statement that was formulated in the 80s and 90s and so on, this is very much derived. So this derived algebraic geometry approach was certainly developed by James Scary and Lurie, and is used everywhere here. So how to get a handle on that, I'm not sure what to say, but the constructions that appear here constantly use the theory of derived algebraic geometry in higher category. Although the specific statements, such as the existence of Hecke eigensheaves, is not a derived state. Some remarks, and then I'll.
Joakim?
Yes.
Oh, sorry, I guess, does this equivalence maybe have any, like, is the cohomological amplitude bounded at all?
That's a very good question. So I'm actually thinking a lot about related things. So the answer is, first of all, careful. So this one here is not, for example, the constant sheaf goes to something concentrated in degree, cohomological degree negative infinity. So part of the story is that you now have to deal with objects in some derived category, but each of whose cohomologies is 0, but the object itself is not 0. If you consider the tempered version, then yes, the cohomological amplitudes are bounded. And in fact, you can control it very concretely, I think. But it's not exact. The de Rham statement is not exact. Okay. And some remarks. First about Barkov's question. So we didn't need the full geometric Langlands conjecture. What you need is, first of all, a spectral decomposition, which in this categorical setup means an action of quasi-coherent sheaves on moduli systems on the automorphic category. So you can regard this as the automorphic to spectral direction of the correspondence, if you will. So this was due to Grinfeld and Gates-Curry in 2010. Very much uses, say, the representation theory of Katz-Moody algebras, things like this. That's the first thing you need, and the second thing you need is existence of Hecke eigensheaves for irreducible local systems. This is in some sense the key part of of the correspondence. So this is certainly due to Bailison and Rinfeld to show that in the ROM setup, where you consider D modules, there is a method to constructing Higgs eigensheaves which are not present in, say, when working over a finite field, and that's the access to representation theory of Katz-Moody algebras. You can construct the Higgs eigensheaf using localization and the relationship between Katz-Moody representations of Katz-Moody algebras and operas due to Fick and Frankel. Bailison and Rinfeld, that was maybe a kind of a non-derived statement. Gates-Square made it derived, and then can prove the existence of generic opera structures. This is what you need to make it work. The spectral decomposition gives you the decomposition, and then you need to know that W sub sigma is non-zero, which is taken in this, I should say. I also proved this in the tame case, which I'll remind you, this was all a lie. You should do this for punctured curves, and then you need these statements. Two more remarks. So if you can generalize this to the case of wild ramification, then this shows that rigid local systems are exponentially motivic, or I would say exponentially motivic, meaning the following. Just when you work with local systems that don't have regular singularities, well, it couldn't be motivic in this state, in the sense I wrote in the beginning, because it was the push forward of some constant sheaf, so we would have regular singularities. And so there's a question of.
But now your local system, it's a V module or something.
Sorry, yes. So sorry. I'm using, if you have a vector bundle with an irregular connection with irregular singularities. Yeah. That's what I mean by a local system here. Then this would show that it's built out of the exponential D module on A1. So as I understand it, there's a question of what should be the suitable analog of being motivic when you consider vector bundles with irregular singularities. And there's kind of a proposal of, well, it should be built out of the exponential D module, which is reasonable if you think of that as the analog of the Schreier sheaf in the finite field setting, say. And this perhaps witnesses that it's not a bad notion. Okay, I think that's the most. Okay, I'll stop here.
Are there any questions?
In the same case, can you give some example for a group which is not VLN or between local system?
Yes, so I didn't prepare matrices that would realize this, but I mean, one important example where this geometric Langlands correspondence also enters is is when you want to construct analogs of Fusterman sheaves for general groups G. So maybe you want some local system on G, which is rigid, so it's determined by its local monodromies, and it satisfies analogs of the Fusterman sheaves, majority, and maybe some equidistribution and so on. And these were constructed by Yun and Heinloth, Nobel Chow, using the geometric Langlands correspondence, for example. So that's one key point where this kind of analysis enters already.
You mentioned the word tempered. What does it mean here?
Yes, and that's a good question. It has various definitions, and I probably won't be able to motivate them from the usual definition. One definition
You do, I mean, at some point, I'm just now interpreting your Katz moody, are you doing some analytic continuations from that of certain?
I wouldn't say that ever enters the philosophy, no.
And is there some Hilbert space decomposition that's, is there some Hilbert space theory somewhere that comes into this theory at all?
So, no, but I'm sure there's precise analogies to be made. One definition is that it's exactly those sheaves that admit Whittaker models.
It sounds circular. Yeah, okay, all right. So by the way, the Whittaker model seems to play a very big role then in this geometric Langlands. They build in the Whittaker as part of the story. Or you
Yes, very. So in fact, the functor itself is given by
the Whittaker.
Yeah, I mean,
Interesting.
maybe to say a better answer to your question about temperedness, the kind of original definition uses the derived syntactic correspondence, and there it's characterized by having kind of considering sheaves that are not concentrated in degree negative infinity in the T structure. So that to me is a statement about, yeah, I'm not sure if I can incorporate some analysis in that, but that's somehow not, there's something to say there. I can't do it. Yeah.
If G were GLN, is there any intersection at all of this approach to what was already done?
I don't see it. I don't see it. For example, one very interesting question to me that I don't think anybody has considered is, what does middle convolution correspond to under geometric Langlands? It seems like a very, very interesting question, and I don't know about that. Yes, I don't see an overlap. So for example, I
Middle convolution sounds like it's connected with tempered.
In particular, I wouldn't know how to obtain the other known results, for example, that appear.
So classification for your local system, probably very hard.
Say again, sorry?
Can you classify, is there a hope to classify for your local system, like the?
For a general group?
Yeah.
They are classified for GLN. By Nick.
No, I'm, so even for kernel group?
Sorry.
He asked for any other group.
Oh, any other group? No, I don't see it. I have no idea. Somehow these middle convolution procedures induct on N, and I would have just no idea what the statement could even be somehow.
Even for classical groups?
Even for classical groups, I'm not sure. Maybe there could be something to say about like SON or something, but yeah, I don't have anything to say about classification for other groups.
I mean, you could have a GLN local system where the image of pi1 is actually inside, say, an SON or an SPN, if that is even inside that GLN, the same N.
Mm-hmm.
Okay. So, I mean, it's not clear a priori that this object thought of as a G-local system with a smaller group is even rigid. In this
Right,
sense.
right. Yeah.
So
Right.
what's going on?
Yeah, right. I'm not I'm not quite sure what's going. So what you're saying is if you take, but also the other way around, if you have a rigid G local system, and then you embed G into some GLN, and the induced rank N local system won't be rigid necessarily. And so it's not clear how to probe the general group case from GLN. And I guess it says something about the notion of being rigid is difficult to relate to GLN somehow.
I mean, it's plausible that if you have your local system on G, your general G, that some condition on every pushout from every representation of G toward G or something, some set of conditions on all those
Right.
is in fact equivalent to the original thing being rigid. I mean, if you know all those pushouts, you know the original object.
Yes.
Pretty much.
Right. Yeah, I guess I don't know what conditions you would impose.
Just by curiosity, here you start with V. To what extent can the story be repeated if you start with a local system of groups on X?
I mean, I would say just if you allow G to be, certainly in the tame case, so where you allow G to generate to the Vohori, for example, then this can be repeated. And the thing you have to address to make this work for other groups, local systems on the curve, or wild ramification, is a local story. So what needs to be developed is somehow purely local. But the method itself should generalize if you have enough control over things like the decomposition.
So how important is it that you use the Durham version?
That's a good question. So that was remark 3, but I ended up not writing it. It's tantamount. So this won't work in other. There's a lot of other geometric Langlands categorical equivalents. There's a petty one where you consider just, instead of vector bundles with connections, you consider topological local systems. So geometric Langlands corresponds for that, and that won't work for these considerations. One way to see that is that the affineness of the moduli would give wrong statements. And so there's something very interesting about the Durham case, and that is you can take the Motivic D modules over here and ask properties about it on the spectral side. That's somehow unique to the Durham. The short answer is it's a Durham story.
This statement is still true.
These statements are still true, yes. But for example, I used for example, that the thing that the structure sheaf corresponds to is Motivic, and that will fail in any other setting.
So there is no X version of this.
Saying there's no Higgs.
Yeah, I mean, if I want to rather than consider the RAM local system, it's
I guess the Higgs version would seem more reasonable. I'm not sure how, so given Hitchin duality, I would arrive at this motivicity statement. But the Higgs version does have the property that it's kind of it shares similar features. In that sense, it's more reasonable, yes.
Where did quasi unipotent play a role in?
That's a good question. So that's again relating to the lie that we took everything on ramified. So the quasi-unipotent from this perspective comes from the fact that imposing conditions at infinity is about how you're considering twist sheaves on bungee with level structure that are equivariant against the character of the torus. You want that character to be motivic. You want that to correspond to a torsion point. That's where it comes from. So one sees that quasi-unipotence is very natural from this point of view.
So if you have like other like local monodromy at infinity, can you say like it's motivic respect to that like that monodromy? So, like it's given by Fishford or from like.
I don't know. No, I don't know what to say. Being motivic is not a local condition for me. Yeah. Everything is motivic locally, analytically, or something. Yeah.
Can you reprove? I mean, can you go beyond the case of curves, or it's impossible? Like, for example, can you reprove from this perspective the correlate Simpson's result?
No, so I mean that's a very appealing thing to try. I don't see it at all. And in fact, I was going to state some conjectures related to that, and somehow I'm getting increasingly pessimistic about the truth of these conjectures. And
but what's the main obstruction? I mean, it's more like what's the missing?
I mean, you could, okay, so let me just maybe say, suppose you had some smooth, proper, complex surface X. Maybe I should use another. So Y, smooth, complex surface. You take some curve inside of it, which is a surjection on pi 1. Right? So conjecturally, you should be able to detect whether a local system here is motivic by pulling it back to the curve. Very much open, I would say. The map from X to Y induces a map on local systems on Y, which sits inside local systems on X. So now you can ask, under the geometric Langlands correspondence, what does it take for a D module to be supported over the subset? I have no idea. So what you would want to prove is some kind of motivic condition, some sense. I have no idea. So maybe if Y is the product of curves, you can say something, but in general, I'm not sure. I'm not sure there's anything to say. I don't know. I shouldn't say that. I don't see it. I don't see it. Yeah, it's not very really solid.
Well, sorry, I guess related to your remark too, if I have like a rigid local system in the usual sense, will it still be an isolated point in the like wild moduli stack?
No, I mean you want to fix the conjugacy classes at infinity. So if you consider the modular space of vector bundles with connections, imposing the monodromy also tells you whether it had regular singularities or irregular singularities. So I wouldn't think so, no. Yeah.
Where you are in the world case, the condition at infinity is that the complete and should be something given.
The condition there, what do you think?
I think
Yes, I think you want to impose that the vector, when you restrict the vector bundle around the punctured disk, that it gives some specific local system on the punctured disk.
But
maybe that's too strong. Maybe that's too strong. That
You really want to deal with Stokes business?
Yes. That's fixing the Stokes data also.
Yeah.
yeah. I'm not quite sure about what exactly is there. Yeah, you would want whatever
Thinking the hypergeometric case to understand it when you put the completion on the
right, yeah, that's yeah. I suppose you want the condition that guarantees that its tangent space gives you H1 of the H1.
So let's thank Joakim.